So I ended yesterday's webinar with this slide, and so I wanted to recap everything we covered yesterday are techniques to calculate a target pressure, and using that target pressure and comparing it to the measured pressure, we can calculate the difference or the excess pressure here. Using those same techniques, we can even calculate a factor using the HEI method, and that is called the cleanliness factor. And the cleanliness factor is kind of a misnomer because there are a lot of mechanisms that can cause indicated low cleanliness factor. And we classify causes of performance degradation into these 6 categories shown here. Now, fouling, everyone should be familiar with, and that's with how dirty or obstructed their tubes are, and that can increase condenser pressure. Also, if there's lower flow rate through the condenser than what is being used for a cleanliness calculation, then you can have an indicated low cleanliness factor. But there's also a whole other class of degradation mechanisms, and that's called air storage. And air storage is pockets of low to moderate partial pressure of air that greatly reduce the heat transfer. If you go back to one of the earlier slides, it was that first layer of thermal impedance that the steam has to penetrate to get through to the cooling water, the cold cooling water to condense. And you know, everybody's familiar with problems of high air in leakage and how air in leakage can cause condenser pressure to increase. But similarly, so that's high air in leakage, but similarly, ineffective venting can cause back pressure to increase. So what this is examples of this are vacuum. If your equipment is vacuum equipment, is LRVPs, then a damaged impeller or high seal water temperature will decrease air offtake flow rate from the condenser, and that will cause condenser pressure to increase. If the vacuum equipment is steam jets, then perhaps low motive steam pressure or high intercondenser pressure on the discharge of your steam jets are cause for lower air offtake flow rate from the condenser, and that also can increase condenser pressure. Even vacuum equipment piping, the piping that leads from the condenser to the vacuum equipment, the layout of that piping can also contribute to air storage in the condenser. And I'll show you how that can be measured as well. Now, this mechanism we call ineffective venting, and that can cause excess back pressure. The last category is air binding, and whole condensers have had modular replacements because of this issue. Air binding occurs in the bundles, and air removal sections that were poorly designed to begin with allow pockets of air to exist at all operating conditions. It doesn't matter really how high the vacuum equipment capacity is or how low the air in leakage is, these pockets persist and cause excess condenser pressure for all operating conditions. And after I present some slides on excellent ways to monitor fouling, I'll present measurements of air binding in different condenser designs, and I'll also present projects with 1 to 2 year return on investment to correct these design deficiencies. Now, yesterday we discussed the left side of this tree for basic performance analysis. Today we're going to discuss the right side of the tree. Now, these 3 condenser performance degradation mechanisms that I just talked about are the focus for this advanced analysis. So they're shown here, fouling and non-condensable storage. Inundation is another one that I'll mention. And now the goal here is to determine how much of the performance loss is due to each of these mechanisms. And once that is known, then the justification and correct maintenance decisions can be made. So listed below each of these degradation mechanisms are tools that can be used to quantify or monitor each degradation mechanism. And so I want to describe each one a little bit. Side stream monitors, they sample the cooling water and they draw that out into a system that is outside of the condenser. And inside there, it creates a simulated environment where scaling or biogrowth is measured by mechanical or thermal sensors. And through this measurement, the potential for microfouling in the condenser tubes is inferred. So that's that instrument, that tool to monitor microfouling. There's other tools to monitor macrofouling. We highly recommend using water box differential pressures. I'll show some examples of how this is made and talk about the right way to make this measurement. There's also tube monitors. Tube monitors can be also used to monitor fouling, and there's other uses for tube monitors. Now these are instruments that are installed on the outlet, in the outlet water box, on the outlet end of the tubes, and they monitor individual tubes. And this is a method that ASME PTC 12.2 recommends for quantifying fouling, and we have made some improvements on some of that instrumentation to monitor fouling that I'll talk about in the next couple slides. Those instruments can also measure inundation. This is a design, a factor of the design. This is water that creates that resistive layer on the outside of the tube and impedes heat transfer. So you can do some inundation analysis with that. I wouldn't recommend that for operating and maintaining a condenser, but for objectives of if you were looking to improve the performance through a design retrofit, then that's an important aspect to quantify. Now, as we move over into non-condensable storage, there are different ways to monitor that. Almost every condenser gets shipped with rotometers on the discharge of their vacuum equipment, their vacuum pumps or steam jets, and that you can measure the non-condensable flow rate leaving the vacuum equipment. And so that's one method. We highly recommend using a REAVAC instrument, and we'll talk about what that is. But it's an instrument that goes between the condenser and your vacuum equipment, and there's a lot of more useful information that you can get from this measurement, and we'll talk about that. Also, condensate chemistry measurements can also help identify identify air and leakage and identify the location of air and leakage. And so I'll spend a few slides talking about condensate chemistry measurements, how to interpret them, and the reason for air and leakage affecting some of those measurements. It's good to have a fundamental understanding of how condensate chemistry measurements can help you troubleshoot and locate air and leakage. So first, let's tackle fouling. Now, the best way to address microfouling is to, number one, monitor it, and number two, to prevent it. Controlling fouling is an endless battle. Water chemistry changes over time, and the chemical process that works today will at some point not be enough. I guarantee that the condenser will macrofoul and go unnoticed, and potentially go unnoticed until tubes begin to fail. So we encourage people to monitor fouling, use the early fouling detection methods that I'll show you, and protect the condenser tubes. It's challenging to quantify the benefit of preventing failures, but if you can implement these techniques, you definitely will increase the life of the condenser as well as the performance. So some recommendations from the ASME performance test codes is to use a ball cleaning system. So, in addition to to cooling water chemistry programs and good layout practices, they recommend the use of a ball cleaning system to satisfy the cleanliness requirements for a performance test code test. There are some other inspection type methods for monitoring fouling. We'll kind of skip over those. They also recommend single tube or tube monitors to monitor fouling, and we'll talk about those in a couple of slides. So first, let's talk about microfouling, and then we'll talk about macrofouling. Now, microfouling is a film that builds up on the inner surface of the tubes. This film could be calcium, it could be manganese, those are common ones. It could also be just dirt or biogrowth, and it increases the thermal resistance between the cooling water and the ID of the tube. So that reduces heat transfer coefficient. We've already talked about that, and there's some typical sources of that. And so I want to talk about tube sheet monitors to monitor microfouling. Shown up here in the upper left-hand corner is the device recommended in Performance Test Codes 12.2. And we've made some improvements on this device. This device is simply a thermocouple attached to the outlet of tubes in the outlet water box. We've improved considerably on this concept with high density temperature arrays, which I'll talk about in several slides. But for now, I want to focus on a technique that we use to monitor microfouling, and that is the use of a flow meter. This is a single tube flow meter shown here on the left side. Okay. It uses a thermal dispersion technique to measure flow rate. The meter provides an unobstructed flow path for the water, so mechanical cleaning, projectiles, and balls from ball cleaning systems, they pass right through it. Heat transfer is calculated on individual tubes using the inlet temperature from a separate measurement, and outputs from this instrument, which are flow and temperature. And so with delta T across given tubes and the flow rate of the cooling water, you can calculate very accurately heat transfer coefficient. Now it's attached to the tubes using the same epoxies that are used to coat water boxes and tube sheets. Both of the tube sheets shown in this diagram, this coating here is actually has scale deposited on it. This black color indicates that it's a calcium and manganese containing scale. And then here's another tube sheet with a clean coating of plastic-core material, an epoxy that's used to commonly coat tube sheets. We use that same material to attach meters to tube sheets and coat the cables. And here's just a little simple video showing how this device, just conceptually, that here's a single tube monitor device with a cable, and it just essentially gets fitted into the expanded end of the tube that is expanded and rolled into the tube sheet, and it provides a completely unobstructed path through the condenser tube. It's essentially an extension of the condenser tube. So now I want to show you some measurements from this device. Here on this graph is the cleanliness factor for a condenser. Here we'll take a look at the y-axis. Here's cleanliness factor that's calculated using the bulk techniques that we talked about yesterday, the inlet temperature, the bulk outlet, pressure, and I believe flow rate was used to calculate this cleanliness factor here. Now you'll see that there's data missing in these time periods here because all of this data has been filtered for only high load. This condenser is a peaking unit. It's up and down all day long, and so we've taken out the data that's below probably 90% load. And so here you can see this cleanliness factor over a month-and-a-half time period. And one thing to notice here is if you you probably all have access to data similar to this on your condenser. You can see kind of this shift in cleanliness right here at about somewhere in the early August here. And so if you're monitoring using bulk techniques that we described yesterday, you would identify this time period as an event that caused the cleanliness to decrease. But this unit also has single tube flow meters on it. So we don't know at this point if this is due to an air leakage event, a sudden increase in air leakage. We don't know if something happened to the cooling water flow, or if maybe a bunch of debris got through onto the tube sheet. So you can't tell. You can tell the magnitude of the problem, but you can't tell what's causing it. But since we had single tube meters in on this unit, I'm going to plot now the cleanliness factor calculated for each tube that's being monitored. So this data has been this data is from meters that have been operating for over a year, so there's quite a bit of variation in the data due to buildup of debris and scaling in the individual tubes. Notice some of the values are not all at 100%, some are above, some are below. Because some of these meters are installed on the periphery of the bundle, some are deeper in the bundle where the heat transfer is a little bit lower, and some of them are located on the periphery of airbound zones that we were studying in this condenser. Now what's important to track is not so much the absolute value of each one of these, outputs of each one of these, or the calculation from each one of these meters. It's more the trend. This changes over time. And so one way that we use to look at the trend of macrofouling is to take an average of all these meters. And so that's what's plotted here. So now we've faded into the background the absolute or the calculations from each individual meter, and now we're plotting the mean of all of that data. And so here's what you see. So before, in the bulk cleanliness, we'll go back a slide. So right about here is where that cleanliness seems to have taken a sharp jump. But now we see, looking at the single tube cleanliness data, you can see that it's pretty clear that microfouling started to occur several days earlier, maybe even back here. And the trend is almost it's a consistent trend downward from this July, looks like maybe July 26th, 25th time period down this way. And so really now, not only do we know that the reason for the cause for decrease in cleanliness, we know that it's not air leakage, we know that it's not macrofouling. By looking at the individual heat transfer coefficient for these monitor tubes, we can see a consistent downward trend in the cleanliness of these tubes. And so now you can take a look at your chemistry program, or if the ball cleaning system is not operating or whatnot. So that concludes microfouling. Now let's move on to macrofouling. Now macrofouling is different than microfouling. Macrofouling is debris that's too large to fit through the tube, or maybe gets lodged within the tube down the length of the tube. And the cooling water pushes this debris up onto the tube sheet over the tube inlet, blocking flow of cooling water through the tube. And so you can see some really bad macrofouling here. This is a chip scale from the ID of the pipe and water box that's made its way onto this tube sheet. There's also, I believe, some mussels, shells here also mixed in with this debris. Here's another unit that pulls in a lot of silt, sand, and again, freshwater clam or mussels debris. And this is collected at the bottom of this water box here. And so I want to talk about some monitoring techniques to quantify and trend macrofouling in the condenser. So a really nice project that we did with EPRI and Southern Company at Plant Yates is some of the data that I want to show today. We partnered with, like I said, EPRI, Southern Company, Clean Air, and Intech to conduct some of the tests that I'll talk about here and publish a report that you can find. If you're EPRI members, you can find it. Here's the EPRI report here. And also a lot of this data was presented at the Condenser Technology Conference in 2014. That's probably the best conference to attend if you're a condenser system owner. That technology conference is once every 3 years, and it has excellent papers on it. But I want to talk about the test that we did at Plant Yates. We wanted to test these single tube flow meters in an operating unit for a long period of time. So this project was a 2-year project, and we conducted this test at almost the 1-year mark. What we did is we wanted to purposely macrofoul the unit. So just before the unit was scheduled to come down, to come offline, we injected oversized cleaning balls, sponge balls, into the cooling system with the intent of them lodging up and causing something similar to what you see here, but with oversized cleaning balls. There's some of the details here. We injected several charges of the balls. They were added into the system at regular intervals. And the size balls that we used were here, and the hardness of the balls were a standard hardness. And they were the tubes in the condenser were 21 millimeter ID tubes, 7/8 tubes. I think they were 24 gauge titanium tubes. And so let's take a look at some of the data from these signal tube monitors and data from the DP monitors, which we highly recommend for quantifying macrofouling. Oh, so yes, this is a schematic of the condenser. There's the inlet here, inlet cooling water. It goes through the bottom half of the condenser, turns around in the back side of the condenser, and flows back through the top half. Yeah, so there's more details here. This is what we call the first pass of the condenser and the second pass of the condenser. And so we'll look at data from meters, both that are installed on the first outlet of the first pass and meters that are installed on the outlet of the second pass. Okay, and so this is an image to give you an idea of what we expected to happen. This is a photograph of the lower half of their tube sheet. And after the test was done, I crawled into the water box and manually inserted these tubes for another reason. And I took several photographs of the tube sheet here and stitched those photos together and corrected for parallax. And I created this image after the test was completed. And so this gives you an idea of what we hoped would happen, that these oversized balls would get lodged into the inlet tube sheet. So let me show you the data and show you what actually happened. So here on this graph is the flow rates is shown here on the left y-axis. And so that axis corresponds to all of this data up here, the thin green and thin red measurements from each individual flow meter that was installed on the tube sheet. Then we also have on the second y-axis, this is the number of tubes obstructed by the balls, and the data is shown in the thicker yellow and blue lines. The bright yellow line corresponds to the number of tubes obstructed in the first pass of the condenser. The dark yellow line corresponds to the number of tubes obstructed in the second pass of the condenser, and the dark blue line is the sum of both the light yellow and dark yellow lines. And so let's take a look at the raw data, and then I'll tell you how we calculated the number of tubes that were obstructed. Here's the raw data. The red lines are from the meters in the B path, through the condenser. The green lines are through the A path. We injected all of the balls into the A path, only one path through the condenser. And so you can see here that when we did our first injection of these balls, the flow rates in the second pass went down because we're obstructing tubes. The total flow is being reduced. But look at what we saw here. And this is what you would also expect is in the first pass, when those tubes get obstructed, the total flow now has to go through fewer number of tubes, and so the velocity increases. So both this decrease in the second pass, this increase in the first pass, those are expected results of obstructing these balls in the first pass of this condenser. But what we did not expect to see was this downward slope here and this upward slope. And very early on in the test, it became apparent that these balls, even though they were oversized, and the supplier who recommended them thought they would get lodged and not travel through the tubes, they were actually traveling through the tubes, leaving the first pass and getting lodged in the second pass, and leaving the second pass and going back through the cycle. So they were actually still making their way through the tubes throughout the test. And so what we did is use these velocities to calculate the number of tubes obstructed by the balls. And so that's what's shown here in the yellow and blue lines. And so you can see here that the first pass immediately gets obstructed. That's why it shoots up to about 1,100 balls, which is what we inserted. I think we inserted 1,000 actually on the first injection. And they obstructed the first pass, but eventually they made their way through the bundle and started getting lodged in the second pass. Then we injected, I think 2,000 or 2,500 balls, I remember the results added up quite well, but I think it was 2,000, 1,000, 2,000, 2,000, 2,000 is what we did. And so, and you can see here when we inject the second time, again the balls go in and they obstruct the first pass and begin making their way through the condenser and obstructing the second pass. And so these this calculation using the velocities, the single tube flow rate velocities, added up very well to the total number of balls that were in the system. And then at this time period right here, we turned on the collection screens, and the balls started getting collected over time, and they eventually all came out. Now this is one method to monitor macrofouling, but the method that we would recommend is using the differential pressures. So there's a right way to do this, and it's often not enough to monitor just one DP for each path, to monitor just the inlet and outlet, because there's hydraulically the different paths are tied together. And so what you need is both a differential pressure across each path, as well as a differential pressure monitoring the flow rate through the outlet nozzle. And so with both of those DPs per path, those are shown here. We've got a differential pressure on the A path and a differential nozzle pressure on the A path, similarly with the B paths here. And so if you plot the differential, or the ratio of these two measured values, you can calibrate this output to the number of tubes that are obstructed. And so the ratio of the differential pressure across the condenser over the differential pressure across the nozzle is shown here in this magenta color. And so this is the same time period as the ball injection test, and you can see here that you see the first injection of 1,000 balls, then 2,000, 2,000, and 2,000. And it's a very good way, it's an inexpensive way and a very good way to monitor the number of tubes that are obstructed from macrofouling. But it does require some know-how how to install the DPs to make sure that they are going to remain unobstructed, the taps are unobstructed over time, and then to calibrate if you want the actual number of tubes obstructed. And so we talked about how to make this this tap, how to locate these taps, and how to install these taps to avoid some of those maintenance issues. We talked about that yesterday. So that concludes fouling. Now we want to move on to non-condensables in condensers. And so there's different ways to monitor air inflow into the condenser. You can monitor it on the vacuum equipment. There's a couple of things to monitor when looking at when monitoring non-condensables in a condenser. Number one, you need to know the vacuum equipment capacity, because if the vacuum equipment capacity is low, that can cause the back pressure to rise. It has the same effect as high air linkage. And so we recommend monitoring the vacuum equipment capacity. And to do that, you need a measurement on the suction side of your vacuum equipment, be it steam jets or LRVPs. And so the only tool on the market available to do that is the REAVAC instrument, which we'll talk about in a slide or two. The other parameter to monitor is air in leakage. And there are different ways to make this measurement. There's the suction side measurement, which measures air in leakage with the REAVAC tool. And then there are other methods. There are discharge side. When I say discharge side, I mean meters that can be installed on the discharge of your vacuum equipment. And so there's differential producers that can be put there. There's the rotometer, which probably everybody's familiar with. You can also put a bag over the discharge and measure the bag volume fill over time. That's one way to measure the air in leakage. Or there's electronic flow sensors. We actually developed an electronic flow sensor early on. It's simple thermal dispersion meter, but we found this measurement to be more useful and more reliable. So let's talk about non-condensables and condensers. Oh yes, one last thing I wanted to add here. Air storage detection. So monitoring air storage detection, you need tube sheet monitors to to measure air storage in condensers. So let's talk a little bit about what air storage is. We have a kind of a saying in Intech that air and leakage is not a problem. It's air storage that's the problem. And it's meant to be a provocative statement, but it's significant if you can understand the difference between air in leakage and air storage. Air storage is the cause of back pressure increasing that most people associate with air in leakage. And so let's talk about what air storage is. Well, air storage occurs in two different ways. There's a stagnant zone, and these form at the air removal section inlet. And this is caused by air and leakage exceeding pump or steam jet capacity. And so pictorially, I have a condenser shown here on the lower left. Here's a condenser shell with a bank of tubes. You can see the air removal section here in the center region, and a stagnant zone forms in and around this air removal section. Okay. And if your vacuum equipment capacity decreases, this stagnant zone will grow to a larger size. And if you increase the vacuum equipment capacity by turning on another pump or decrease air leakage, then this stagnant zone will shrink. And so the way to attack or to correct excess back pressure from stagnant zones is really maintenance. Reduce the air leakage or increase the vacuum equipment capacity. The second way that air can be stored in condenser is air-bound zones. And these are configuration caused due to the configuration of this shroud or the configuration of the bundle or lanes within the bundle. Air collects away from the air removal section over here. And this section, this air-bound zone has to grow to a certain size where the periphery of this bound zone reaches the air removal section, and that air can be removed with the vacuum equipment capacity. Now, in both types of air storage, if the tube is located in an air storage zone, here or here, then the cooling water enters the tube at the inlet water box, travels, say, 30 or 40 feet through the condenser, and condenses very little steam, very little to no steam. And it exits the tube at a temperature well below the expected value. And so, tube sheet monitors are the way to measure the size of these air-bound zones. And I'll show those in a couple of slides. So let's first talk about the ReaVac tool. Again, it gets installed in the air offtakes. So here would be a good location for one, or here, or in the common line leading to the vacuum equipment. And it measures these parameters. It has four primary measurements. It measures the total mass flow, the absolute pressure, the relative saturation, and the temperature. And with these four measured parameters, we can calculate the dry air flow, the water vapor flow, the volumetric flow, which is useful for LRVP capacity measurement, or and you can use the total mass flow for comparing steam jet capacities to their manufacturer specifications. But the most useful parameter that comes out of this tool is this one right here, the water to air mass ratio. And I want to talk a little bit about why that is. If we go back a slide, the water to air mass ratio, it gives you the state of the gas vapor mixture at this point, which directly correlates to the size of this air-bound zone in the condenser. So if the air-bound zone is very small, then the water vapor to air mass ratio is high. If this zone is very big, then the water to air mass ratio at the air offtake is very low. And so that is a single parameter. This parameter right here is a single parameter that can tell you if air is affecting the performance of the condenser. And we'll see why that is in the next couple of slides. So first I want to talk about the overall effect of air on condenser pressure. And so to do that, I'm going to use this, this relationship, pressure versus air and leakage for a given operating condition in a condenser. And so what I first want to point out is that is with no air and leakage, a condenser should operate, let's just take for example, at 2.5 inches. That's the best it can operate with no air and leakage. And as air and leakage increases, back pressure should not increase because the vacuum equipment capacity can handle it. There is no stagnant zone, no appreciable stagnant zone forming in the condenser. It's not air binding many tubes, and so the pressure stays constant. And then there reaches a point right here, this knee, where the stagnant zone expands into the bundle, and now tubes outside of the air removal section are being blanketed and heat transfer is impeded. And so above this point, as air and leakage increases, the condenser pressure increases. And so this line here, this curve that I've been highlighting, this is the stagnant zone response to air and leakage. Now a condenser with air-bound zones, for very little amount of air and leakage, an air-bound zone is formed. And so the back pressure increases for very little amount of air and leakage because there is a zone, there are a number of tubes blanketed by air. And so now you have a similar response, whereas air and leakage increases, there may be a slight slope upward here, and then it reaches this knee, and now you have both a stagnant zone and an air-bound zone. So this equation over here is an equation that we use for more advanced studies where we want to calculate the excess back pressure due to different mechanisms. So the total excess back pressure is equal to the excess back pressure due to air and leakage, high air and leakage, plus the excess back pressure due to ineffective venting, which is right here, where this knee moves, plus the excess back pressure due to configuration of the design of the condenser, and then on top of that is fouling, the excess back pressure due to fouling. So now I want to show an example of how the RIAVAC tool can be used to quantify air and leakage and identify the location of air and leakage. And we'll take a look at some of the parameters from this instrument. So here is a unit that we deployed some RIAVAC instruments and some other instruments too. This condenser was just newly commissioned, and the performance of this condenser was not where it needed to be. And so they knew the condenser pressure was above the design value, but they didn't know what was causing it. They didn't know if it was fouling, air and leakage, whatnot. What they really wanted to know is if air and leakage was affecting the condenser's performance. And so this unit was in India, and so we shipped some instruments over. We had some engineers go over, and we installed RIAVACs at each offtake from each one of these bundles. So this is the condenser. There's two shells here. There's an alpha shell and a bravo shell. And each bundle has an offtake here, 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 and here. They combine and they go to a single set of vacuum pumps, and we had RIAVACs installed in each one of these offtakes. So I want to show some of the data from this. Now during the data that I'm going to show you, we were monitoring very, very small flow rates over here in this location, and the client was not believing the measurement, so we moved it over to the common line that went to the vacuum pump, and so I'll show you the data from these measurements. So here they are. RIAVAC 1 was measuring 40 SCFM of air and leakage coming from this bundle, 4 SCFM from this bundle, 2 SCFM from this one, and 47 in the common. And so we calculated this value over here using these other 3 measurements. And so moving from this B bundle to the common line, everything added up perfectly. Customer was very satisfied with this. But here, let's take a look at what information we can gather by having these measurements on the suction side of the vacuum equipment. Number one, we can see that air and leakage is very high in this bundle and low in the others. Also, we can see that they're operating one vacuum pump, and most of the vacuum pump's capacity is on this one bundle. We have a 1/10 of the capacity here, and a 20th of the capacity over here. And so this bundle is dominating most of the pump capacity. And so, since the air and leakage is here, the pump capacity is here, we know that this is causing an issue, an imbalance in the flows leaving the condenser. What else we can tell is that the water-to-air mass ratio is very low. We'll see in a few minutes that if this value is below 3, then we know there is excess back pressure in the condenser. And so with these measurements, the client was confident that air and leakage was coming in somewhere in this north wall of the condenser, going through this bundle, leaving this air removal section, and so they were able to narrow their search for air and leakage. And here's the data from these probes. Now this is a little bit busy. What I want to call your attention to is a few things. Number one, here's the air and leakage here. This red line is the air and leakage from that north bundle. Here is the air and leakage total here. These red lines. And during this time period, we turned on another vacuum pump. So right here, we turned on a vacuum pump, and you can see the total volumetric flow rate increase. We go from 1,500 cubic feet per minute all the way up to 2,500 cubic feet per minute. So we've turned on a vacuum pump. We've gone from operating pump B here to pump A and B here, and then pump A over here. And what we immediately see is what's shown up here on the very top of the plot is condenser pressure. We can see the condenser pressure reduces a little over 1/10 of an inch here, or 5 millibar. And when we go to one pump operation, the condenser pressure increases. So here we have proof positive that the air and leakage is affecting the condenser pressure. Now, I made the comment earlier that the water-to-air mass ratio, if we go back to this slide, the water-to-air mass ratio here, this teal line here, I've made the comment that this number, this value, this mass ratio is proportional to the number of tubes being blanketed by air. And so you can see that pictorially here in this diagram, the stagnant zone here. The size of this stagnant zone and the number of tubes blanketed by air is directly proportional to the water-to-air mass ratio measured by the RevVac equipment on the air offtake. And so if you were to plot condenser performance or cleanliness factor versus water-to-air mass ratio, which we did for this unit, so we plot the water-to-air mass ratio versus the cleanliness factor, you get this relationship here. And this occurs for every condenser out there. You can create this characteristic curve and know exactly how much performance is lost due to air and leakage in the condenser. This relationship exists for every condenser out there, and sometimes the knee occurs, kind of right here at a value of 2. Sometimes it's out at 3. Sometimes it's back here at 1. But this relationship exists for all condensers. And so our rule of thumb for all users of this equipment is that if you have a water-to-air mass ratio above 3, then you have no excess back pressure due to air and leakage. So here's a graph which you'll find in your handouts that's kind of a reminder of how to interpret this plot. There's the water-to-air mass ratio of 3, below which you have stagnant zone formation, above which there's no stagnant zone, and this distance or this separation between your measured performance and the 100% line is base performance degradation due to scaling or fouling or airbound zones. So let's talk a little bit about air storage measurement. So now those are the tools that you can use to monitor air storage in the condenser. This is a way to actually measure and see the airbound zones in different condensers. And so this is, I want to talk about, or I want to show you these measurements, how we make them, and then show you some of the results in actual condensers. So again, here's ASME PTC 12.2. Here's the figure that they recommend for measuring outlet temperatures on condenser tubes. And let's take a look at this. So here's a condenser. The ideal condenser you would expect. Here's the inlet water box over here. Here's the outlet water box over here. And you would expect cooling water to come in at a cold, say 70 degrees on the left side, travel through the condenser 30-40 feet, and exit at maybe 20 degrees higher. And you would, in the ideal case, you would expect this temperature rise to be uniform on every single tube. But that's not the case. We know that some tubes perform better than others, and sometimes the water goes through the condenser and the temperature increases 0. And so here's a unit that we monitored. This is a De Laval condenser. Over on the left you can see there's photographs that I've stitched together of the outlet tube sheet. You can see some instruments that we've installed at these locations here and here. This is during the installation process, so there's still some tools on the tube sheet that will be removed. But the instrument that we've installed here is this instrument. It's a high density temperature array. We're measuring temperatures at every single tube location. Actually, there's 2 temperature sensors for every single tube all the way along this length here. And so what we're doing is using the temperatures measured at this location to get the water temperature exiting these tubes. And it's a very high density temperature array. And with that, here is shown over on the right are the locations of these instruments. And the color map that you'll see here is the temperature rise across this condenser. So blue is a 0 temperature rise, and 21 is a 21 degree Fahrenheit temperature rise for this condenser. And so we use a program to interpolate all of these measurements using a model that we have to interpolate between all of these different points. And this is the temperature map for this particular condenser, and you can see right away the way I like to look at these plots isn't really in the temperature mode. You know, we can see here that there's 0 temperature rise here, there's about 14 degrees temperature rise here, but what's more important is to look at the performance profile. How do these temperatures compare to what the temperature rise that they should be getting? And so if you can take this temperature profile and turn it into a performance profile. And so that's what's shown here. 0 is 0% cleanliness factor or heat transfer, and 113 is 113% of the HEI value. And so you can see here the performance profile of this particular condenser. And one way I like to look at these is to identify the yellow color, because it's easily identifiable. Yellow corresponds for this particular plot of about 75% cleanliness, and you can kind of see the boundary that it draws around this area, and that is an area that's affected by inundation and air in this particular condenser. Now, inundation won't get you down to 0%. This is really the effects of air binding in this region here. So here, here, and here, these are all air-bound zones, and this in here is the air removal section. This is a stagnant zone here. And so there's other ways to monitor air binding as well. We've developed another instrument it's a string, a temperature string. It's a very small OD string that we thread through individual tubes. The OD of the cable is about 1/8 of an inch, and it gets strung down the length of tubes. And what these black dots are here is a Westinghouse condenser where we've installed instruments inside the tubes and on the outlet tube sheet. And the black dots represent a location for each and every temperature sensor in this study. And so we've been able to create a complete three-dimensional model of this particular Westinghouse. And here's the temperature profiles using this technique. So now we can monitor air binding not just from an outlet tube sheet perspective, but we can monitor air binding in the third dimension throughout the condenser. And this provided us for this project some very useful information to design a retrofit to get rid of this air binding. So again, this is the temperature profile for this particular Westinghouse. This is the performance profile of this particular Westinghouse. So we take all that temperature data, we apply the HEI formula, and we can calculate per bay or per unit length the cleanliness factor for the individual tubes. And so again, if you take a look, if you take that yellow color that I talked about, the 75%, you can kind of start to see the airbound zone, the boundary of the airbound zone for these Westinghouse condensers. For the by the way, this is an upper bundle in the upper half and a lower bundle in the lower half. So this is what air binding looks like in different condensers, and I've shown you air binding in two different condenser designs, and we'll talk about how to get rid of those air bind zones later on in the talk. But this is what air binding looks like. And so now I want to talk about, I want to show you what air binding, how it looks when there's high air leakage or ineffective venting. So we'll show you how these airbound zones shift over time. We'll show you a movie of an airbound zone growing and shrinking over time through a test. So this is a Foster-Wheeler condenser design that we monitored air binding in. There's two shells in this particular condenser. We'll take a look at the data from, I believe it's this shell here, and we've got temperature sensors all over this thing, and we'll take a look at the performance profile. So here's the performance profile of this particular bundle, and now I'm going to animate this slide, and you'll get to see the airbound zone forming. And just to give you a little background information on this particular bundle, this bank of tubes over here is the designer's air removal section. This is the air removal section over here. This over here is the airbound zone that we've identified. Remember, an airbound zone is a bank of tubes that's not in and around the air removal section, that's blanketed by air. You can see that the temperature rise here is very low. We're getting less than 20% heat transfer in this area over here, and all of this area is affected by air. And so what I'm going to do now is animate this slide to show you what happens when the vacuum pump capacity got decreased in this unit. So here it goes. I'm going to animate it, and you can see what happens to this airbound zone. Okay, so this is the performance profile. Again, this is not a model. These are direct measurements. This is a performance profile map created using temperature measurements. It's not a model. And so here is now the airbound zone and stagnant zone. They've joined together to make this massive area of blanketed tubes in this particular condenser. Okay, so now we'll come back to air binding and non-condensables, but I want to talk about condensate chemistry. A good understanding of condensate chemistry can help you determine if poor performance is due to air leakage or not. It can also help you locate air leakage in the condenser. And so, according to HEI and ASME, these are the condensate chemistry measurements that should be monitored for a good condenser performance program. Condensate dissolved oxygen, cation and degas conductivity, and some other measurements. Okay, so let's talk about condensate chemistry. Where does dissolved gases come from? Where does this dissolved oxygen, and where does how does dissolved gases, how do they affect condensate chemistry? So here, let's take a look at condensate chemistry inside an air-bound zone. So here's our a diagram of a condenser with its stagnant zone here. We're going to blow up on this zone, and there's our stagnant zone that exists in most condensers. And so the condensate that's formed on the outside of these tubes above the stagnant zone falls down and enters this region of high partial pressure of air. Okay, and now these colors don't represent a temperature change, but they represent the increase in dissolved gases in the condensate. So there's no dissolved gases in the condensate up here, and as they fall through this zone, there's dissolved gases in the condensate. And we can quantify that. The way you quantify the amount of dissolved gases in the condensate is using Henry's law. Henry's law is shown here. The concentration of dissolved gas is equal to the partial pressure of that gas in equilibrium with the water times the Henry's constant. And this Henry's constant has a temperature dependency on it. And so the two gases that we're concerned about in most condensers is oxygen, dissolved oxygen, and carbon dioxide. Now, here's just kind of a rule of thumb. 1/10 of an inch of air storage causes about 20 ppb of dissolved oxygen in the condensate, and 1 ppb of dissolved CO2 in condensate. Now, some of the results that I'll show you here on the next couple of slides is information that was presented at the Electric Utility Chemistry Workshop in 2010. This is the title of the paper, and this paper was voted best paper for that year's Electric Utility Chemistry Workshop conference. So dissolved oxygen, or dissolved carbon dioxide, behaves differently than dissolved oxygen. It reacts with the water. And this chemistry is very interesting and can help you identify the location of leaks and identify if leakage is a problem. So what happens with carbon dioxide when it reacts with water is it forms carbonic acid. So here's carbonic acid. And that carbonic acid dissociates into hydronium and bicarbonate. And that bicarbonate dissociates into more hydronium and carbonate. So it reacts with the water. And here are some of the reaction constants for this chemistry. Now, the reaction rates are 1,000 times faster in the forward reaction rate than the reverse reaction. So once the CO2 is dissolved into the water, into the condensate, and has created carbonic acid, bicarbonate, and carbonate, it doesn't come back out before reaching the hot well. In fact, it doesn't even come out until the deaerator or polishing system starts to attack it. And so all this while, the condensate pH is affected. It can dissolve corrosion in the condenser, cause corrosion particulates to get into the condensate. And this is a real problem. These airbound zones can be a real issue as far as corrosion and condensate chemistry throughout the cycle. Now, this chemistry is dependent upon pH as well. That's an important aspect about this chemical reaction. So at higher pHs, more dissolved CO2 occurs. And so the dissolved CO2 content, even though there's very little CO2 in the atmosphere, the concentrations can get very, very high because these reactions occur at higher pH. And so here's a plot that relates the total inorganic carbon, ppb, to conductivity being measured in the condensate chemistry. Now, we ran a test at this particular plant. The way to measure the amount of carbon dioxide dissolved in the condensate due to CO2 dissolution is to take a difference measurement between the D-gas cation conductivity and the cation conductivity. And so we did that. And we were able to measure that the CO2 does in fact stay in the condensate and not come out until much further on down the chain. We also introduced air and leakage into the condensate offtake, So here's a little tiny, let's see. Oh no, this is a rotometer. This is a 40. This is a large rotometer, a 40 SCFM rotometer that we attached to the outside shell of this particular condenser, and we bled amounts of air and leakage into this condenser to monitor the condensate chemistry. And so what our intention was to take the airbound zone in this particular condenser and increase its size purposely by introducing air and leakage. So we went up to 120 SCFM and monitored the dissolved gases in the condensate. And so this is the data. Here's the air and leakage shown in red here, the air and leakage. And the air and leakage value was at about, looks like 80 SCFM it started off at. We went up to 120 in this particular condenser. And as we increase the air and leakage, you can see the condensate dissolved oxygen increase. And more importantly, you can see the condensate pump discharge cation conductivity increase. Now, some condensers have features within them to limit the amount of dissolved gases that reach the hot well. And these condensers are touted as being deaerating condenser. Now, something to note is that a condenser should be a perfect deaerator with a good design. You should not have airbound zones and stagnant zones forming in the condenser affecting condensate chemistry. So while these are good features to have, it can really mask the problem of a design issue up in the bundle, and that's not good for performance. Now, another test that we did was to introduce air and leakage into the condensate flow offtake here and measure its response. And now, to calculate the effect on condensate chemistry, this is really just a mass flow problem. The mass flow of air and leakage entering the stream plus the mass flow of water, you can calculate the amount of dissolved oxygen and dissolved CO2 in the system. And so an underwater air and leakage like this, you'll get a big dissolved oxygen spike, but not much dissolved CO2. And so here's the response of that particular test, where we increased air and leakage into the stream by only, I think it was a few SCFH, and you can see a humongous spike in dissolved oxygen and not much change in the cation conductivity here. And so here's the summary of all this condensate chemistry, is that by taking a look at the condensate chemistry, you can identify the location of the air and leakage. So a cooling water side leak, you'll have high sodium, high cation conductivity, high degas conductivity, and almost no or moderate dissolved oxygen. If you have a steam side air and leakage, so air and leakage above the water line, then you'll have low sodium, high cation conductivity, low degas cation conductivity, and moderate dissolved oxygen. If you have an underwater air and leakage where that air is entrained in the offtake, most commonly we see this at the condensate pump isolation valves. If you have a leak through the stems there, or maybe an underwater manway, then everything will be low here as far as conductivity measurements, but you'll have very, very high response for very, very small levels of air and leakage. So that concludes all of the instrumentation for both basic and advanced studies. So I want to show some case studies where now all of this instrumentation has been put into place, and we've identified issues with condensers and implemented retrofits and increased the performance of these particular condensers. So this slide is a nice summary slide for the instruments that we would recommend for various reasons. Differential pressures for flow and macro fouling, a ReaVac tool for monitoring all non-condensable related degradation mechanisms, pressure, temperature, and then tube sheet monitors for taking a look at the design of a condenser. This is our first case study. This is a condenser with, this is a 90 megawatt condenser with a side steam inlet here. It's got a history of higher than expected turbine pressure. And the project we did a basic engineering evaluation where we identified some performance deficiencies here. Then we installed instrumentation that I just showed on the previous slide, and we implemented a condenser retrofit. So I want to talk about that. Here's the condenser from a side view. Here's some of the instrumentation that we installed to get the performance profiles. Here is an air and leakage test that we ran on this particular condenser. We purposely introduced air and leakage here, 5 SCFM all the way up to 120 or 60 SCFM. And here's the performance profile. Now, this particular condenser had a lot of microfouling on top of some air binding, and so that's why this performance profile is not in deep red here. You can see here's the air removal section here. Here's some air binding out here, and out here extending out of the air removal section, and then most of the condenser had some microfouling as well. And so here's the air and leakage test, where we formed a stagnant zone and airbound zone, increased the amount of air binding in this particular condenser. Let's move on to this particular condenser. Here's an Ingersoll-Rand air storage here. This is an Ingersoll-Rand condenser with air storage that we've monitored. Here's a Westinghouse that we've looked at before. And here's the De Laval. So I want to talk about each one of these projects. Some of the best times to address some of these issues is when the condenser is being retubed, because we have the most amount of access to these condensers. We can, the tubes are removed, we can build new air removal sections in them, we can target the areas for the best performance upgrade. And so those are the best times for retrofit. But some retrofits, which I'll show you in the next couple slides, you can address some of these performance issues without a retubing. The tubes stay in place, and we can vent out the regions that need to be vented without pulling any tubes. And so this is the approach to doing it. There's a 4-step approach that we've used. There's a basic performance evaluation where we do a component inspection. Then there's step 2 is instrumentation, where we would install basic or advanced instrumentation into the condenser to evaluate its design. Step 3 is to use all of the data from the advanced instrumentation package to evaluate the performance and engineer a solution for a particular condenser. And so here's some slides that talk about each step in detail. I'm not going to go through all of this here, but you can take a look at that on your own. Otherwise, I'd just be reading it. Here's a photograph of some materials that we've used for a 600 megawatt retrofit. You can see that the materials that we use are standard carbon steel plates, piping, and essentially what we'll do is we'll bring air removal to the areas that need to be vented better. And so it's really not much material, but there is engineering required to figure out where to build these air removal sections to eliminate these airbound zones. Here's a schedule on a typical schedule for implementing a condenser retrofit project. Typically, they span about 1 year to 2. There are certain milestones that have to be met. The most important ones revolve around condenser inspections, doing internal inspections for instrumentation and for retrofit purposes. So those would be here and out here. And some economically strong drivers for heat rate improvement via condenser modification of these. If your station is looking to uprate, if there are seasonal or permanent heat input limited operations, then a retrofit will not just decrease the unit heat rate, it will actually increase total generation of the unit. Variable frequency drive cooling water pumps, that's not very common, but if you have these, in the wintertime when the condenser pressure reducing condenser pressure doesn't gain you much in heat rate or generation, you can actually throttle back on your cooling water pumps earlier in the season and save station power and deliver more power to the grid. Any units with cooling towers can benefit from a condenser retrofit as well, because typically the inlet temperatures are much higher than closed cooling systems. So let's talk about each one, some case studies. Here's one of our first case studies. This is a 400 megawatt, Ingersoll Rand unit. It has 2 shells, 2 passes. It's an open cooling water system. It has a persistent macrofouling problem. We installed an advanced instrumentation package including tube sheet monitors. This is the one that we've seen before. It was this tube bundle. And so we addressed 2 major issues in this particular condenser to improve its performance. After doing the study, we identified this airbound zone here, and we were able to use the techniques that I showed you on previous slide, the water-to-air mass ratio versus cleanliness curve, and the air binding performance profiles to determine how much excess unit heat rate was a result of the air binding, as well as macrofouling and ineffective venting. And so this plot, using all the techniques that I've shown before and the relationships that I've shown before, we calculated the total unit excess heat rate, and we're able to calculate the individual excess unit heat rate from macrofouling, air binding, and ineffective venting. Now this particular unit, the majority of the performance loss was due to macrofouling, but during that condition, their bundle became undervented, and so the macrofouling actually exacerbated some of the air binding in this condenser. So we made 2 major changes in this condenser. One was external to the vacuum equipment piping, and another change was to the condenser bundle itself to bring that air bound zone closer to the air removal section. And so here's the results. During the outage, the material was the condenser tube material was changed from Admiralty to stainless steel. We also had the opportunity to change the pattern of the stainless steel tube sheet. Now we didn't change any of the support plates, but we did change the tube sheet pattern, and we added about 1% condensing surface area. We eliminated the airbound zones. We moved the air removal section to something more traditional, more shrouded, centrally located air removal section. And this new bundle allowed for future projects to implement a 100 reversible flow configuration to handle debris macrofouling. That would be for a future project, but several changes were made here, both internal to the condenser and external. And so here's the results down here. Pre-retrofit, the unit was fouling and air binding to the tune of operating all the way down to 35%, from 35 up to 75%. The mean performance factor over that time period was 50%. And the mean condenser pressure over that time period was 2.8 inches. After the retrofit, after all of these changes were made, we got rid of some of the air binding, we reconfigured the external piping. The performance factor range over the same time period was 75 to 90%. The performance factor mean was 80, and the condenser mean pressure was 1.8 inches. Now here's another project, an Ingersoll Rand retrofit project. This bundle, the Ingersoll Rand bundle, was modified during the outage. They did some turbine work. The unit was retubed, but the tube material did not change. They originally had copper nickel tubes. They retubed with copper nickel tubes, and they installed a condenser retrofit. Now in this condenser retrofit, this case study, we have both before and after performance profiles that show the marked improvement in condenser performance here. And so this is a really nice case study. Here's an advanced instrumentation package that we installed before and after the retrofit. Here's a layout that you can take a look at. We have test grade temperature sensors, both on the outlet, the turnaround. So the cooling water comes in this direction, turns around and enters the HP condenser. We have REOVACs or PTs monitoring both the hot and cold end of each shell. We have REOVACs monitoring the vacuum pump capacity out here. And we have water box instrumentation here and here monitoring the performance profiles. And so here on the left is a performance profile before the retrofit for this Ingersoll Rand condenser. This one was particularly bad, very bad air binding. This is the air binding profile with only 18 SCFM of air and leakage, very low air and leakage. If you use that yellow boundary technique that I talked about earlier, here's the yellow boundary that kind of defines the size of the airbound zone here. You can see it's quite large, encompassing more than half of the surface area. Post-retrofit is shown here on the right. We actually took out the existing air removal section that was here, and we built a brand new one in the new bundle during a retubing. And so this is the performance profile obtained at 27 SCFM. So here's almost an apples-to-apples comparison both before and after the retrofit, an 18 SCFM performance profile on the left and almost 30 SCFM performance profile on the right. And so we have some really good measurements on this condenser. What I wanted to show is an animation showing what these performance profiles look when we purposely introduced air and leakage to the bundle before the retrofit and after the retrofit. So I'm going to animate these slides as we increase air and leakage. I'm going to take this left bundle up to 155 SCFM. I'm going to take the right bundle up to 100 SCFM, and we'll see what we get. So here it goes. Here goes the animation. And remember, these are all measurements. These are not models, but these are actual performance profiles created from the actual temperature measurements on the tube sheets. So here you can see before the retrofit, now the airbound zone is grown quite large, encompassing probably 90% of the bundle. You do see, using that yellow technique, the heat transfer start to get affected by air in this particular condenser, but you can see the blue area is very well confined to this new air removal section, whereas before it's kind of spread out all over in the condenser. And so not only is this condenser performing better even from the low air and leakage standpoint, it is also performing better from the standpoint of air and leakage immunity. This condenser can handle up to 100 SCFM without appreciable excess back pressure. And so here's some of those numbers. In the before condenser case, increasing the air and leakage from 15 to 65 SCFM, the back pressure increased 0.8 of an inch. Huge excess back pressure from 4.5 inches. And the dissolved oxygen increased 12 ppb. Post-retrofit, we went from 40 SCFM up to 100 SCFM in only 0.2 of an inch. Only 0.2 for this high air and leakage that was put into the condenser. And the baseline condenser pressure was lower at 3.6 inches. Also notice that the condensate dissolved oxygen was much, much less for this even larger increase in air and leakage, because we've essentially confined the air to a much smaller space within this condenser. It's much more immune to air and leakage. And so here's some more data from that same case study. What I'm going to show here is on the y-axis condenser pressure, here on the y-axis the cooling water inlet temperature here on the x-axis, and what you can see here is the LP shell pressure, the low pressure shell pressure here shown in blue dots, the high pressure shell here shown in red dots, and this is for year 2006. We performed the retrofit in 2010, the end of 2010, and so what I'm going to do is click through some slides here showing the data 2006, 2007, 2008, all the way up through 2011, and show you the dramatic back pressure reduction after this condenser went through a condenser retrofit. So here we go. There's 2007 data. Here's 2008 data, the whole year of 2008. In 2009, the condenser had a vacuum pump problem, so they had to vent or exhaust both shells using one vacuum pump. So the LP shell and the HP shell became common pressure for a short time, and so that's why you see the LP shell operating up at the HP shell pressure. In 2010, that problem was fixed, and so you can see the HP shell pressure came back and the LP pressure came back to its normal operating cluster there. At the end of 2010, we implemented the retrofit. The unit came online in January 2011, and look at this dramatic improvement in condenser pressure because of the changes we made in the condenser design, eliminating those airbound zones. A dramatic difference in condenser back pressure. And so if we do some trend lines between this data, you can see that over an inch of mercury was reduced in the HP pressure, over 0.6 of an inch was reduced in the LP pressure, and that corresponded to about an 80 BTU per kilowatt hour permanent decrease in their unit heat rate, or an additional 6 megawatts in their summertime. Here's some more information if you're interested about the air and leakage immunity. Some things that I want to point out are we talked about the dissolved oxygen increase being much less for large amounts of air and leakage increase. And then what's added here that wasn't on the other slide is the cation conductivity increase. Almost no cation conductivity increase due to dissolved CO2 after the retrofit, but there was quite a bit of increase before the retrofit. If you compare this to industry guidelines, in the performance test codes 1998 version, a unit of this size with this amount of flow rate, that's what this unit had, they recommend that this unit should only operate with 4.5 SCFM, only 4.5. But now this condenser can operate with almost 100 SCFM with very little excess back pressure. Also, the HEI 10th edition guideline says that if you have air and leakage greater than 40 SCFM, you can probably get these high dissolved oxygen content in the condensate. And we've just shown on the previous slide that there's almost no dissolved oxygen increase once we get rid of that air binding in the condenser. This is that case study that I talked about earlier, and this is what I really wanted to show is something different. This is, we did address some air binding in this condenser, but there was another aspect of this condenser that we found by putting this instrumentation on the condenser. We found an opportunity to reduce the turbine exhaust pressure in this particular condenser. So this is a 90 megawatt condenser with a side entry turbine exhaust. It had a history of higher than expected turbine exhaust pressure. There really wasn't anybody monitoring this or looking for performance improvement. And when we put some test grade instruments on here, we found something truly unique, and I wanted to share that with you. This particular unit, they plan to increase the duty to the condenser 35%. And the plans were already implemented when they found out that this condenser would be a bottleneck to this process. So they kind of had their backs up against a wall. They committed to this additional steam being emitted to this condenser, and so they were looking for ways to improve the condenser pressure without having to completely replace the equipment. And so we did a basic engineering evaluation, an advanced engineering evaluation, and performed a different kind of condenser retrofit here that we found using some of the test grade measurements that we installed. What we found was that here's the sparger. This is a sparger in this turbine exhaust duct here. And we had access to a steam temperature and pressure measurement upstream and downstream of this this turbine exhaust tunnel, and the temperature and pressure measurements correlated quite well. And what we found is that they were losing about 0.8 of an inch just in this duct because of the conditions of the steam that it because of a pressure drop that occurred across this steam drain or steam bypass into the condenser. We confirmed it with CFD. The CFD matched very well to the measurements that were made over various operating conditions, and so it was a pretty simple fix to reduce this pressure drop from the turbine exhaust to the condenser. We implemented a turbine exhaust duct modification to increase this area and reduce that differential pressure across this turbine bypass pipe. And so we lowered the turbine exhaust pressure by 0.5 of an inch by implementing this this design. And now with all the changes that we made in this particular condenser, the condenser is operating below the trip point, even in warm weather, which was not possible with the original design. This is another unique condenser retrofit. This is the De Laval condenser. This retrofit we performed without any other work to the condenser, so there was no retubing, there was no turbine work. It was just simply our condenser retrofit project. And so we installed several measurements. You're probably familiar with this two bundle design here. So here's the pre-retrofit performance profile. For low air and leakage, very low air and leakage conditions. We've identified these airbound zones pre-retrofit in the 4 bundles here. And so what we did is we installed piping and baffles to extract this air without doing a retubing. So we worked around the existing tubes, and you can see here the dramatic improvement in the airbound zones post-retrofit. Again, if you use that technique where you identify the yellow color to identify the boundaries of this airbound zone, you can see how big it is pre-retrofit and how it's dramatically reduced post-retrofit. And so here's the results from that particular retrofit. There's condenser pressure over on the y-axis. There's cooling water inlet temperature on the x-axis. And pre-retrofit data is shown in red. This is post-scraper cleaning. They had a ball cleaning system, kept their tubes very clean. Pre-retrofit is shown here in the red data. Post-retrofit is shown here in the green data. And something to note here is that their air and leakage actually increased during this outage. It was an unfortunate thing that occurred, but their air and leakage actually almost doubled over the course of performing the retrofit. But despite that higher air and leakage, we got 0.2 of an inch pressure decrease, and if this air and leakage gets reduced, this back pressure should go down by another 1/10 or 2. So this slide here, I'm coming towards the end of my slides. This slide here summarizes some of the options that you would have to improve the performance of your condensers. There's modular replacement, there's retubing, and retrofitting. And this table is modified from the Heat Exchange Institute's tech sheet 122. You can find that on the web. And here's some comparisons on capital cost. Most of the projects that I showed to you today were completed with under $1 million worth of investment. So most of those projects had about a 1 to 2 year return on investment. And that's where we really try and target the value to people with underperforming condensers. If they have a bundle that's underperforming that has air binding, you know, we're looking at solutions that we would try and develop solutions that have a 1 to 2 year payback. So it's a lower cost option to some of these other ones. Performance, you can get improved back pressure, increased output generation with the retrofit, and and really any time is a good time to perform these retrofits, but the best time really is concurrent with a retubing. And because that's when we have the most access to the bundles to incorporate the best configuration for air removal. So in conclusion, poor condenser performance is often blamed solely on cleanliness, but it's really often a result of many different factors. And what we call putting a microscope on your condenser, putting test grade measurements on the condenser, allows you to quantify the impact of individual performance degradation mechanisms. And that data can be used to make informed decisions, rectify those mechanisms that are economically viable, and allow you to go forward with your condenser maintenance programs. Many condensers designs remove air poorly and they operate much less than their potential, and those designs can be fixed with a retrofit, providing significant increase in condenser performance. So that concludes our presentation on condenser performance essentials. If there is any questions or anything, I'd be happy to take them. Otherwise, if you have questions later on, you can contact me or Colin by email, and we'd be happy to get back with you.
Okay, well, thank you very much, Tim. We don't have any questions submitted yet, so I guess we'll just end the session now. And if you have any questions, you can send those to us later. So again, thanks very much, Tim.
Thank you, Randy. My pleasure.
Okay. All right. Bye, everyone.